Have you ever stood under a clear, dark sky and wondered where it all ends? It is a question that feels as old as humanity itself. We look up at the countless stars scattered like diamond dust across a velvet cloth, and our minds naturally drift towards the idea of forever. The night sky stretches out in every direction, and it seems to go on and on without any sign of a boundary. One of the most powerful reasons to think the universe might be infinite comes from a simple idea: its shape. When cosmologists talk about its shape, they are not talking about whether it is star-shaped or cube-shaped. They are talking about its geometry, which describes how things move through space on the very largest scales. There are three basic possibilities. Space could be positively curved, like the surface of a sphere, or it could be negatively curved, like the surface of a saddle. The third option is that it could be flat, with no overall curvature at all. Think of it like this. On a sphere, the angles of a very large triangle add up to more than 180 degrees. On a saddle, they add up to less. On a perfectly flat sheet, they add up to exactly 180 degrees. Scientists can perform a similar test on the universe itself, using beams of light that have traveled for billions of years. When they do this, their measurements show that our universe is remarkably, almost perfectly, flat. Now, why does a flat universe suggest it might be infinite? A flat shape is the only one of the three that can go on forever in a simple way. A sphere is always finite. A saddle can be finite or infinite, depending on other properties. But a flat universe can be imagined as an endless three-dimensional plane. If it is flat and keeps going, it has no end and no edge. It would be infinite in size and volume. This is the simplest, most direct interpretation of what our best instruments are telling us. Another compelling argument for an infinite universe comes from a theory about its very first moments. This theory is called cosmic inflation. It proposes that a fraction of a second after the Big Bang, the universe underwent a period of astonishingly rapid expansion. It grew from something unimaginably small to something astronomically vast in less time than it takes to blink. This sudden and violent stretching of space is not just a fanciful idea. It helps to solve deep puzzles about the universe we see today, including why it appears so flat and uniform in all directions. Imagine you have a small, crumpled, wrinkly balloon. Visual diagram. A small, wrinkled ball rapidly expands into a huge, smooth sphere. Visual diagram close-up. A tiny square on the surface of the huge sphere looks flat. If you could inflate that balloon to the size of the Earth, the patch you are standing on would look incredibly flat. You would not perceive its overall curvature. It is like the ocean looking flat from a small boat, even though we know it follows Earth's curve. Inflation suggests the part we can see is just one tiny, flat-looking patch of a much larger reality. The full universe could be trillions upon trillions of times larger than what our telescopes show. In many models, expansion might not have stopped everywhere at the same time. It might still be happening in distant regions, creating new universes in an endless, bubbling cosmic foam. In this picture, our universe is part of a process that naturally leads to an infinite or near-infinite cosmos. Inflation makes an infinite universe feel less like philosophy and more like a consequence of early universe physics. It suggests our finite world is an island of calm in an infinitely stretching ocean of space-time. For many physicists, this is the most elegant explanation we have for why the universe looks the way it does. Sometimes the simplest evidence is the most powerful. When we look out with our most powerful telescopes in every direction, we see more or less the same thing: galaxies, clusters, and vast empty voids. The universe appears isotropic, the same in all directions, and homogeneous, the same average properties everywhere. If we lived near an edge, we might expect a different view one way versus another. But across the sky, the statistics match. No cosmic wall, no end-of-the-road sign. Of course, this does not prove infinity. A finite universe could be so large that we are like a microbe in the Pacific, seeing water in every direction. Still, an infinite universe explains this straightforwardly. If space has no end, we would not see one. Science often favors the explanation with fewer special conditions. Now, let us gently consider the alternative, that the universe is not endless. A positively curved universe could be like the surface of a sphere, finite area, no edge. Walk straight, and you eventually return where you started. Our universe could be the three-dimensional equivalent, a three-sphere, closed, finite, boundaryless. Fly perfectly straight long enough, and you could come back to your starting point. In such a universe, space, volume, and the number of galaxies are limited. Our measurements show very close to flat, but very close is not exactly. There is always a margin of error. It is entirely possible the universe has a slight positive curvature, too small to detect today. Like surveying a tiny patch and calling Earth flat, our observable region could be one patch of a gigantic, closed cosmos. Flat might be an illusion of limited perspective. This possibility remains on the table. There is another way the universe could be finite, even if it is perfectly flat. Topology studies how spaces connect. Space could wrap around on itself, like an arcade game, fly off one edge and reappear on the other. Finite world, no boundaries. Imagine a three-dimensional donut, a torus. Travel straight and eventually return to your start. Look far enough and you might see another image of the Milky Way as it was long ago. A multiply-connected universe would act like a hall of mirrors, creating repeating patterns in the sky. Scientists search for these patterns in galaxy surveys and in the cosmic microwave background. So far, no convincing repeats, no cosmic hall of mirrors. The fundamental domain could simply be larger than we can observe. The most important evidence for shape and size comes from the cosmic microwave background, the afterglow of the Big Bang. It is a snapshot of the cosmos at about 380,000 years old, when light was released and has traveled ever since. The map shows tiny temperature spots, minutely warmer and minutely cooler, the seeds of today's galaxies. The apparent size of these spots is a direct clue to geometry. Larger on a sphere, smaller on a saddle, a specific size if space is flat. WMAP and Planck measured them with breathtaking precision. They are exactly the size expected for a flat universe. Flat to within about 0.4%. That precision still leaves room for a tiny curvature, a gigantic closed sphere too gentle to detect. The echo of creation tilts the scales toward flatness, and possibly infinity, but leaves a small important window open. Another way we probe shape and scale, we make maps of the universe. Projects like the Sloan Digital Sky Survey and the Dark Energy Survey measure positions and distances of millions of galaxies, building a 3D cosmic web. They use baryon acoustic oscillations, a standard ruler, to test geometry. The results tell the same story as the CMB. On the largest measurable scales, the universe appears flat. No repeating hall of mirrors signatures have been found. Maps cannot prove infinity, but they push any possible finiteness far beyond our current horizon. There is a boundary to what we can see, not in space, but in time. The universe is about 13.8 billion years old. Because space has expanded, our observable sphere has a radius of about 46.5 billion light-years. We are trying to judge the size of a room from its center without seeing the walls. It is possible the universe is flat and infinite. It is possible it curves back on itself. It could even have a complex wraparound structure. We can never perform a direct measurement to prove space goes on forever. Evidence can support infinity but not prove it absolutely. Evidence points strongly one way, but science remains open and humble. So, where do we stand? Is the universe infinite? The most honest answer, we do not know for certain, but the evidence leans toward an infinite universe. Our best measurements indicate flatness. Cosmic inflation naturally produces universes that are infinite or so vast they are functionally infinite. This is the standard, simplest model. It fits the data without special conditions. Yet tiny, undetected curvature could still mean a finite, gigantic three-sphere, and topology might be complex beyond our reach. Ultimately, whether finite or infinite, the universe's scale humbles us. Perhaps the beauty is not only in the answer, but in the deeply human act of asking,